We'll now move on to our next presentation. The presentation is Unrolling the Loop, Elastic End-to-End Redundancy, and this comes from Technica Engineering. Three speakers. We have Iago Alvarez, Romà Pagès, and Lars Völker. So please welcome the Technica team for this next presentation.
Hi. Could I get the slides, maybe?
Oh.
Anyhow, let me welcome you, everyone. Hope you have a good morning. And in our talk, we are trying to discuss something we have been discussing for a long time, because there's so many solutions out there. How do you then do redundancy in a network? And we try to make it easy. And I heard already other people said, like, oh, I've done the same thing a couple of years ago. So don't expect us to have done something crazy. It's something that others have done before, I heard. So there we go. So why is everyone talking about loops and redundancy? And we all know that a couple of use cases that really make sense, right? So brake-by-wire, steer-by-wire, some autonomous driving features. Redundancy might make a lot of sense. Often we see system-level redundancy, meaning that it's not like an Ethernet-only redundancy thing, but maybe you have a CAN and an Ethernet at the other side. So that's not a use case we can really solve, right? We can only solve on a system level. However, there are some use cases where the high bandwidth of Ethernet is really needed, and where we don't have an alternative to Ethernet. And for such use cases, redundancy on Ethernet makes sense. So we try to figure out if there's a good solution out there already, and if not, how we can improve that to make a good solution. Let's see what you guys think. So if I typically look at what is existing there, we all know those things, right? Spanning tree, which tries to react on a link breaking by activating another link. We have ring protocols out there. In certain industries, they're very comfortable used and also react kind of a spanning tree. And we also have what in automotive people are considering is 1CB. So where we have really some redundancy for a certain part of the network. It turns out that all of those three solutions have some limitations. So you cannot just put them in the car and be happy. But the thing is, you have to figure out if they really work for you. The first two, for instance, they have to react. Is it okay for you that, you are using one link, and if it breaks, you're trying to switch to the other link, and it might work, might not work. You don't know before, right? So maybe that's not good, right? Because you don't know if the other link actually is working where you're not using it yet. Is it okay that for 1CB, you typically design in a single point of failure? Is that really redundancy? If there's a single switch doing the replication, for instance, and that one fails, then you don't have redundancy anymore. So there's a couple of things where we would say, like, sounds like redundancy, but it's not complete redundancy. So there's some limitations, as you can see on the slide. And then, of course, I could always go and take the biggest solution ever. I run 2 complete networks, like in an airplane, right? Do complete A-B redundancy, everything doubled up, but who wants to pay for that? So we were thinking, can we do something better than that? Can we have a solution that is more cost-effective than running everything besides, and easier than some of the other solutions here, and then also fixing some of the problems? And let's see how we can do that. So, since that would be too easy, we thought we have a little wish list, what things we want to reach, right? So we want to have a scalability over vehicle architectures. If you build a small vehicle up to a big vehicle, you might have some components in a big vehicle, but not in a small vehicle. So we don't want to have different architectures, but we want to have a scalable architecture. We want to have something proactive so that it's redundant, like CB, at all times. So if one path breaks, the other is already working, and you know that it's working. We want to monitor both of them. We want to really the safety guys always do, like with ASIL requirements, where you have an end-to-end monitoring and supervision. We want to have the same for every path. So we know as an application that one of the paths broke, and we can, still try to fix something, maybe do a minimum risk maneuver, try to fix the situation somehow. So we need that as well. And we think for saving money, of course, it also makes sense that we don't have any ASIL requirements on intermediate systems, more specifically on switches. Do I want to run ASIL D software on a switch for the redundancy if I can avoid it? I wouldn't do that. Maybe you have the same opinion, maybe a different one, but we try to avoid that. Let's see if we can do that. And then, of course, we don't want new semiconductors, right? We all have the chips already. If we can do it by our software without changing the hardware, that would be wonderful. So another thing we put on our wish list And then minimize cost, right? It's an important thing anyhow, so we try to minimize risk and cost. So basically, that's the reason we were looking for kind of a ring, kind of a loop, and let's see for a certain zonal architecture, we want to go ahead and connect like our HPC nodes and our zonal nodes with kind of a ring to have some redundancy there. So question is, can we achieve that? And for that, Iago will tell us a little bit about the solutions.
Well, hi everyone. Thanks a lot, Lars. And I would like to go now through our technical proposal to solve this elastic end-to-end redundancy solution. So, what is the main concept behind our solution? The basic idea is that we want to create a ring with traffic sent by the ECUs connected to the ring being sent on both directions. At the same time, the applications running on those ECUs, they need to send the redundant data and they need to monitor such streams via end-to-end protection. How are we trying to benefit from this approach? Well, first of all, we want to create a proactive system. That means, like Lars said, we will have no reaction time whatsoever. And at the same time, there will be no reaction mechanism that can lead into failure. This solution is also a proven mechanism for safety via this end-to-end protection, and due to its simplicity, we will require minimal ASIL requirements that will therefore, of course, imply no additional cost for the switches. It is also important to remark that for this proof of concept, the assumed traffic, it's multicast traffic, either some IP-based or signal PDU-based multicast. So, how do you... So, why do we want to create a ring for redundancy in our network? Well, the basic answer is that we want to avoid having single points of failure, right? That a problem in one part of our network will affect our whole system to crash. Within this ring, we can find different kinds of redundancy levels. We can have an ECU A, which is attached to a single switch of the ring on a single link. We can have an ECU B, which is connected to another single switch of the ring on multiple links, or an ECU C, which is in this time connected to two different switches of the ring. I also want to highlight that even though we have this redundancy network created, we can still add non-redundant traffic as we have today. This traffic would just simply flow on one direction of the ring and it will be completely isolated from this redundancy network. I think the main message that we want to present is that we are seeking a solution that is, of course, functional, that it's simple, and at the same time, cost-effective. So, I know what many of you must be thinking. So we just created a ring, and therefore we have a potential loop in our system. So in order to prevent our frames to keep looping in this ring forever, over and over, we need to design a way to drop the frames after they just travel through the whole ring and they're back at the origin switch. And for that, we have proposed different solutions, different options. Our first option is to drop frames by the source MAC address of the sender. The second one is to use a hop counter that is VLAN-based, and the third one is to drop frames by the VLAN ID on a specific input ports. And in the next slides, we will explain a little bit all these three solutions. So the first solution is, like I said, to drop by source MAC address. What is the approach here? We will have a sender in our ring, which is sending multicast frames on two redundant VLANs, right? One VLAN traveling on one direction and the other on the other direction. Of course, these frames will travel through the whole switch, and when they have reached the origin, the place where they have entered the ring, then we just need to drop them, filtering by their source MAC address. Which is the main benefit of this solution? Well, basically the simplicity of the configuration, right? With just some basic filtering, we can do this. We can achieve this quite easily. But on the other side, we can find some disadvantages. So first of all, we need to know all the MAC addresses beforehand, right, in order to create these filters. Then there could be also a large number of filtering rules, depending on the number of participants that are sending frames towards this ring. There is also a different configuration for every switch. Of course, there is the different components attached to each ring of the ring, switch of the ring, and therefore we need different rules. And any change in the topology will require a change in the configuration. So due to this poor flexibility of the solution, we thought if a hop counter could actually solve these problems. And that's exactly what the second solution is about. So using a hop counter that is VLAN ID based. In this approach, we have again our sender sending multicast frames into two different VLANs. For our example, we can see we are using VLANs 100 and 200, which are being sent into the two different directions of the ring. Here in this solution, the switch in which these frames are entering the ring is doing a retagging of those frames and setting an initial value for this counter as VLAN ID. In this example, we are using VLAN IDs 103 and 203. These messages will travel through the whole ring, and at each hop of it, on each switch, there will be a retagging, and this value, this VLAN ID, will be decremented using some sort of, like we would see in a TTL counter mechanism, right? And the idea is to drop the frames when this VLAN ID has reached our, let's say, our zero value, our reset value, in order to know that those frames need to be dropped in order to avoid them to keep looping. Of course, throughout the ring, the switches need to forward this information to the potential receivers, and in this link between the switch and the receiver, there will be, again, another retagging to turn those VLANs into the original redundancy VLANs 100 and 200. Which are the benefits of this solution? Well, first, we have a fixed number of VLAN IDs, and the configuration is the same for all the switches, right? The switch just does a first retagging with the initial value of the counter and drops the frames when this value has reached a certain value. So in this case, the configuration will be the same for all of them. And also, the MAC addresses of the senders here do not apply, do not matter for us, because all the configuration, all the filtering mechanisms, and all the rules are VLAN ID based. And on the other hand, we can state a main disadvantage, that is that the configuration of this system depends on the number of switches. Of course, for this counter, we have designed the first initial value and the last value based on the number of hops of our ring. So if we include new components to this ring, or if we take some components for this ring, then of course these values need to be readjusted in all the switches. So we can see that this VLAN ID based solution is way better than the first solution that we have seen. But this led us thinking if we can actually further improve this. And that's what we are trying to do in our third solution, which is to encode our input port using a unique VLAN ID. So in this approach, the mechanism is quite similar to the previous one. We have a sender sending multicast frames on two different redundant VLANs, again, 100 and 200. But the switch in which they enter the ring will not do a retagging for this initial value of the counter. It will retag with a unique specific VLAN ID particular for this switch, right? So to identify switch 1, we will be using, for example, the VLAN 101 and 201. Again, these two frames will travel the ring on different directions. Of course, everything that is happening in the ring will be of the form 100X and 200X, depending on the switch that is being sending this information. And the switches will be accepting these frames and forward them to the potential receivers, doing again the retagging to the original VLANs. The key to drop the frames here is that this switch where they have entered the ring needs to acknowledge when the VLAN ID that it has created will be back after traveling through the whole ring to do this dropping. What are the main advantages of this solution? Well, here our ring size can be easily scaled. We can add as many switches we want to this configuration. We can take switches from it because the configuration will just not change. The switches in this case, they do a retagging with its own particular ID, and thus the dropping of the frames based on that ID. So it doesn't matter the number of participants. And also, in this case, the VLAN retagging only happens at the entrance and at the exit of the ring, and not like in the previous solution where we did the retagging at each hop of the network. As a main disadvantage, we can state that the configuration of the switches, so there is one configuration per switch. Of course, here the rules are static for each switch. The switch needs to retag with its own particular ID and do the drop-in of that ID, right? So we will have different configurations per device. So after taking a look at all of these technical solutions, what is the conclusion that we can make so far? The first conclusion is that a redundant ring with today's hardware seems to be possible. We have seen that all the configuration requirements, all the features that we are using are pretty much achievable by any kind of switch that is TC11 compliant. The second conclusion is that we have chosen our third solution for this elastic end-to-end redundancy proof of concept because it allows us to create the ring that we wanted. It's also the most flexible solution, which is quite important to support vehicle variant management. And overall, it has proved to be the solution that has shown the best mechanism and the best approach of the ones that we have analyzed. Nevertheless, after seeing all of this, there are still two questions that remain unanswered. The first one is if all of these things, all of this proof of concept actually works on real hardware, right? And not only on paper. And we have seen in the third solution that even though it's a scalable solution, we can have some complexity, and the configuration of the switches can get them somehow a little bit complex. So how can we face this added configuration complexity? And in order to respond to these two questions, I would like to invite then Romà to take part of the next part of the presentation.
Thank you. Okay, we have our idea. Let's see if we can implement that loop concept using standard automotive switches. For that reason, we built our setup with 4 switches and 2 nodes, and let's see what happened. And we make it work. So using 2 blocks that are found in many switches like VLAN membership access control and TCAM rules, we managed to configure the loops to get the proper behavior. With the VLAN membership list, we can drop the frames at ingress depending on the VLAN. So for instance, in the switch number 1, we can drop VLANs with, frames with VLAN 101 and 201 just when they complete the loop, so preventing them to re-enter again in the loop, so breaking the loop. With TCAM rules, we can do 2 things. We can forward the frames depending on the VLAN, and retag the VLANs at egress. So we can control how the frames enter and exit into the loop. We need 2 rules for direction. So we need 1 rule to inject the frames into the loop and retag them. For instance, in the switch number 1, we need to retag the frames that are coming from the ECU to VLAN 101 and 201. So later on, the VLAN membership access that we have defined in the previous slide can drop the frames and break the loop. We need an additional rule to control how the frames exit the loop. So we need to retag the frames that exit to the ECUs and recover the VLAN 100 and 200 that was originally used for that ECU to send the message. We have 2 directions. So in total, with 4 rules, we can manage the configuration of each rule. And this is the setup you can find in our booth, so you can see how it works in action. You can even disconnect a cable and see what happens. And if you have any question, of course, we can answer in the booth. And now I will turn it over to Lars that will finish with a summary. Sorry.
Thanks, Romà. So we know now what we want to solve. We looked at a couple of approaches. We found one which we liked. And oh, there we go. And we also showed you how to configure it, so we can run it on real hardware that's existing right now. So what you can see is with our solution, we feel that in many of those things, we combined like the best solutions out there. So we are proactive. So both directions are working at the same time already. So if one fails, you're sure that the other is still working because you're already monitoring it. We are in reaction time, of course, like CB. We don't have reaction time, right? Both are working, so it keeps on working. We have full redundancy, and we also have the possibility to detect the degradation as it happens. And this is easily done by having an end-to-end mechanism like we do for air safety anyhow. So it's something that we all have already. We have it in ACLD if needed in the stacks, so it works out of the box. We are pretty sure that if you at least attach the ECUs with more than one cable to more than one switch, you can avoid this single point of failure in the design. And the cost, of course, compared to having completely two networks is, of course, much cheaper and much better. It turns out that we could, at least our wish list we could fulfill, so we think that this solution is much easier than the alternatives. It's already existing, cheaper. So we think it's a pretty good option to consider. There's one open question we didn't answer yet is, as you've seen the configuration complexity that Romà was showing us, how do we solve that? And for that, we don't have the solution today. We're still working on that. But we are considering different approaches here and looking at different tool chains. And what we are looking at is like an AutoSAR XML-based tool chain, which would come with a couple of downsides. We're not sure that we would take that. And we also looked at like other formats like 5X, and I know nobody's working with 5X anymore, so it's kind of dead in the water. We looked at Yang, NetConf, ResConf, CoreConf, all those combinations, where some of the things are in, some are missing, so there would be also some work. But our goals for the tool chain are, as you see at the bottom, that's not what we have right now, but are the goals. So there's a couple of things to solve. For us, we are really aiming for something that is very compatible, fast, and SDV compatible, that can then generate the configuration of the switches. While we have not finished that yet, we are really open to discussion. So if anyone wants to come with us with a good idea, we have a plan actually, we know how to build it, but maybe someone else has a better idea, then come to us, look at the demo, we explain you how it works, and we can discuss the configuration. And with that, well, there we go. Was the last slide, and I thank you for the attention. And you don't have to take the pictures of the slides. If you want them, I can give them to you, all right? Don't worry. Get my email address. Thanks, everyone.
Thank you. We'll start with some questions. I see John is, or is Max first? Whichever.
Okay, hey, thanks guys, nice concept, like it. I'm sure you ran this through a few OEMs. So my point is the single source of failure is the source and the target. So my question is, if this information is so important and we're protecting only the cables because I'm assuming your switches are on the same power supply, I don't know, have you guys had discussions with OEMs whether this effort is worth what we're achieving?
So, that's a good question, thanks Max. So basically we didn't try to solve the problem with the power supplies, right? I mean, if you do system level redundancy, you have to solve that anyhow, right? So what we were aiming at is like a use case that is not quite system level redundancy, but is something where we need Ethernet. Does that mean that it's as good as a real system level redundancy use case? Sure not, right? We agree on that. So yes, we can achieve some level of redundancy, but yes, you also have to solve the problem with the power supplies. You have to think about if the software redundant, do we have more, maybe not one application, but a redundant application. But the thing is, if you solve those, right, you need to do this for every solution, right? And then you can run the data into both of the applications and you can monitor in band what's happening. So it's easier to solve then, if you do not want to use two different methods like CAN plus Ethernet.
Thanks.
Yep. John?
Oh, thanks. It was a great idea. I was thinking about it in the context of 1CB, and that, so you're using VLAN tags instead of R tags, but 1CB is totally transparent to the application, right? So there's like a reconciliation at the low level. So does this impact application software, or is there like a lower layer of software that takes care of the redundant?
You're totally right. 1CB tries to be transparent to the application, but we argue that is the biggest mistake 1CB did. Because if you do redundancy in a car, and I have a function that needs redundancy, I need to know exactly when the redundancy is gone. And 1CB takes away that feature from us. So what you would have to do for 1CB, you would have to add something that communicates exactly that information, meaning that every switch, everyone's involved in that who can figure that out needs to run software. This has to have ASIL B, C, or D, whatever you need, and then communicate that over the stack, also then ASIL, let's say D, to the application, which is a big downside of it, right? That's one of the big problems. The redundancy information, what's currently the state, has to be transparent. You cannot hide that away. And I think that's the biggest mistake that CB did in context of automotive. For others, probably works fine, right? We know the ring protocols for other industries. You don't know either what happens there, but you don't have those kind of high safety goals you want to achieve. And for those, you need to know what's happening right now.
Thanks.
Yeah.
All right. Any other questions? Question? Yeah.
Maybe a redundant question.
There you go.
I don't think it is. Good morning. Thank you again for the presentation. What are the cybersecurity considerations we need to take into account when implementing this and having, the VLAN tag just being changed all the time?
Yes. No, the cool thing is it's basically orthogonal to the cybersecurity. So either you have a solution like MACsec below there, right? And then, of course, you can configure the filters on which VLAN tags are allowed and which you're using. That's totally controlled. Or you have a solution where you say, like, I want the security above it. Then also it's transparent for you. So while in the demo, we have discussed to turn on MACsec to show that it does not have an influence at all. We didn't do that, but easily done. So as far as we have built it, it's orthogonal. You can do your cybersecurity the way you want.
Thank you.
Yeah.
All right, anyone else? Okay, I think we're good.
If they think about a question later, they can come to the booth, right? We are here the whole day. Thanks, everyone.
Thank you. All right, thank you for that. We will move on now to our next presentation.